Hi everybody, this is Professor Chang of Bugyeong National University, Korea. Welcome to my class of image processing. This is my 6th class, image compression. We will talk these contents, image and pixels, image compression, quantization, palette and advanced quantization, and deep learning. Okay, we are here now. You have already studied fundamentals of image processing, versions, image restoration. We skipped color image processing, and last week we talked about frequency domain analysis, and today we will study on image compression. Okay, so what is the image and what is the pixel? Okay, so you see lots of images in this world and in your computer, and if you magnify your photo or your any images, then you will see this kind of shape. Okay, if your image is small, then everything is clear, but when it is magnified, you see lots of zigzags and something which is not much beautiful. This is the pixel. I think you already know about the pixel, but we need to talk about this because we want to speak. I want to talk about the compression. So this is the true image, true color image, we say. To save this image into your computer, we need the space of width multiplied by height multiplied by 3 and multiplied by 4. Okay, and this 3 means this image has 3 channels, R, G, B, right? And 8 here means 1 pixel uses 8 bits to express a color. Here I said a color means R or G or B. So we have 3 channels, and for each channel we need 8 bits. And to express all the colors in a computer, we need 24 bits of space. Then we express a pixel with 24 bits. Then we say that is the true color, because we can express lots of colors with that information, with that space. And to save this image, for example, if the size of the image is 128 by 128, then we will need 393 and 1216 bits, which means 49,152 bytes, and which means about 48 kilobytes. And this is not much, this is okay. Okay, 48 kilobytes is too small, but in many cases, size of the images are not this small. In your cell phone, the image size of the image is very, very big, isn't it, in these days? So if you take a number of pictures and a number of videos, then it will that means that photos will require lots of space in your cell phone. What we want usually is we want to say you buy, let me assume that you buy a cell phone of Apple or Galaxy. Then maybe your cell phone has 32 gigabytes or 64 gigabytes of disk space. but you want to save your photos as much as possible, isn't it? But to save lots of photos in your computer or in your cell phone, then the computer or your cell phone need to compress the images. Otherwise, we cannot save lots of photos in your small cell phones. So we want to reduce the size, but we do not want to lose the quality of the image, isn't it? So we want to reduce the size, but we need to reserve the quality of the image. Then how can we do it? We can do several methods. There are lots of methods in this area and this topic. Today I will talk about the simple things first, and then before closing today's class, I will talk about the pretty new techniques on the image compression. Okay, first you need to understand the classical method of image compression first. The first thing you need to understand is quantization. Quantization is reducing the number of bits for the pixel. Okay, so I already told you that we need 8 bits for to express a color in a pixel, and which means we can express the value from 0 to 255. So if we find any pixel here, that color is expressed from 0 to 255 for R, and another 0 from 0 to 255 for G, and another 0 from 0 to 255 for B. Yes. Okay, then what happens when we reduce these bits? Okay, we can reduce it from 8 bits to 4 bits. Then we have to express the color not from 0 to 255, but we have to express the color with a value from 0 to 15. So we have to express the color of 16 colors only. Then it is pretty easy to implement. We can just map all the colors. Okay, here you can see a graph. If original pixel value is like 92, then it will be expressed into 90. Okay, if it is 94, then still it is 90. And when it becomes bigger, like 100, then it increases suddenly as 110 or something. So we can map all the original pixels to the quantized pixel values. Okay, something strange, isn't it? I told you that it is only from 0 to 15, but I say here, okay, you can express the 92 to 90. Yeah, it is just to explain. We can express 16 colors, and these 16 colors we can choose these 16 colors uniformly according to the y-axis. So the value, actual value, it will be 0 and 15, 30, 45, and blah blah blah, and 255. And this is pretty easy to implement. And this method has a big drawback, demerits. Okay, and this is the result of the quantization. The left of this image left upper image is the original image, and when we reduce the number of bits into 4, so for each channel, then image is going to be like this. Okay, we lose lots of information. It's not pretty anymore. Okay, and when it becomes 3 bits and 2 bits, even the 2 bits for each color, so we can use 6 bits information. We can recognize this is something like a flower, but not that beautiful flower, isn't it? So maybe somebody think this is beautiful, but in general, this image has lost lots of details of the original image. Okay, there is another method. We can use the palette. Palette is a technique of selecting a source of colors to use. Okay, this is a palette. Palette of using 4 bits of information only. Here, 4 bits means only the 16 colors. This is pretty different to the previous one. Here, I said 4 bits here means 4 bits for each color, so each channel. So actually, this is the 12 bits, and this is 9 bits, and this is 6 bits. Okay, here I say this is 16, which means we have 16 colors, which means 4 bits. Here, this is 6 bits, and we lose lots of information. Here, 16 bits, 4 bits. Then the image is slightly better than the previous one, because here you can choose the colors which you want to use it. So if you use the colors more precisely, you can make the image better, actually. So you make the palette first, and then you can express each pixel's color with these IDs only, the ID numbers. So if the pixel value is 10, then which means the color of the pixel is yellow. Okay, this is the palette, and we can save lots of information using the palettes. And this method has been used in the early stages of computer graphics. So long time ago, when I was a kid, it was 1980 something. Then when I see and play computer games, then colors were just like this. Okay. At that time, we cannot use the expensive graphic cards. So this was the best graphics at the time. But in these days, it's not that anymore. So we can use a more expensive one, but sometimes we want to also reduce the size of the images. But this image, this result, is not something we want, isn't it? Because we lose lots of information, lots of important information. So still not good. Then we can mix with quantization with the other method. We can use the color space changing and the quantization together. You already know the RGB space and HSV space already. We have talked a few weeks ago, and we can easily change and convert between RGB color space and HSV color space. Okay. And after in RGB color space, we have to express. We have to use the same number of bits for each channel, because R and G and B are important equally. But when you change this color information into HSV, then we can say the V here is most important, the most important information, because this V information means the intensity of the image. Only with this information we can recognize the original object, but with H or with S it is pretty difficult if you just trying to recognize what it was. So after changing the color space, we can quantize the colors but differently for H and S and V. So we do not quantize V and we use 8 bits for V, but we can do the quantization for H and S. Maybe we used 4 bits for H and 4 bits for S. Then we get this result. Yeah, the color information and the quality of the image has been degraded, but still it's pretty good. We use 16 bits for this image, and the result, the quality of the image is not bad. And when we try to use the 3 bits for H and S and 8 bits for V, then okay, this is not bad. Okay, this is still pretty okay. And when you can compare this result to the previous one, naive quantization. This uses 14 bits, 12 bits, and the quality of the image has been dropped a lot. And 14, and here is 3 and 8 means 14 bits here. This is 12 and this is 14, and you can compare these two images, and you will see the quality of the image here is a lot better, because in this case it preserves the intensity information. Okay, so here you need to understand the basic idea. Divide the information, something important, more important, and something less important. And you can reduce the amount of information for the less information part, and you will preserve all the informations in the more important part. Then you can reconvert and trying to generate the original image. Then we can get this pretty clear image. Then we can extend this idea, and we can use the quantization after dividing the original image into the frequency domain area. Okay, so we can use the Fourier transform, and we can also use the DCT, discrete cosine transform. And this is the result of this discrete cosine transformation. And when you convert the original one image into the cosine DCT coefficient image, then this information has been divided. The high frequency area, high frequency informations are moved into the left upper part, and the lower frequency informations are moved into the right bottom parts. And after dividing the informations like this, we can quantize the image with differently. We may preserve this part and we can quantize a lot in this part. Then we can preserve important information, because in many cases people are very sensitive for the high frequency area and less sensitive for the low frequency area. Okay. So also we can quantize emphasizing more important colors. For example, when we quantize, so in the naive quantization method, we choose the quantized values uniformly according to the y-axis. But here we can choose the quantization parts, and we can choose more points and within a specific range of area, and we can choose a few number of points at the less important areas. Usually, most people are less sensitive during the dark areas, which means that we cannot distinguish the color value of 0 and 1. It is very difficult. And even the color value, you cannot distinguish the color values of 0 and 50. It is very difficult to figure them out. So if we can say we can choose 16 points in this area according to the y-axis, then we may choose just 2 points between 0 and 100, and from 100 to 200 we may choose lots of data, lots of points here. Then we can quantize the quantized image. The quality of the quantized image will be a lot better. Okay, then this is the last part of today's class, and you may heard about deep learning and GAN. Deep learning is a type of neural networks, and in these days it's pretty popular, and this idea has been utilized for many problems in this world, and this is very famous even for non-scholars. Okay, and maybe you have heard about GAN. GAN is a type of deep learning which encodes and decodes the training data and create or generate data, something like the original. Okay, let's see the video.
Dear fellow scholars,
what is the
this
GAN
is 2-minute
can
papers
do.
with
Okay, so this is the generation of GAN. So you see the photo. This photo has been changed, converted into the artistic style, and we can do this with GAN. Also, there are many things we can do with GAN, and this is one example. There is the dancer, and there is a normal people who cannot dance, and this is not the real video, and they mixed and they generated this video with GAN, and they mixed the posture of the original dancer, and they combined together with the participants. Okay, this is what we can do with GAN. This is the internal structure of GAN, and I do not want to explain the detail of the internal structure of GAN because this is not the neural network class. But what I want to say at this time is the input and output of the network structure. Okay, now first let's see the input. Here, the input is the original image, and we put this into the first module, and the first module gives us a vector. which may express the original image. Okay, then the second module will receive this vector and then put the output like this, which means this second module regenerate the original image. So we want to make it possible. So this is how the GAN works inside when we train the neural network. But we do not want to talk about the training procedure of the GAN. But here, what you have to understand here is that the first module works as a compressor, like an encoder, we say. And the second module is working like as if it is unzipping, isn't it? So there is a decompressor, which I mean. So at the first module, we say this is encoder, and the second module, we say this is the decoder, or compressor and decompressor. So here, the information can be reduced a lot by using this encoding network structure. But here is another problem of compressing time. Usually the compressing of JPEG doesn't take much time. It takes only a second, less than a second, I think, when you are converting bitmap image into JPG. But here, if we need to train this network to compress the original image, it may take lots of time. Maybe it takes a day or days. So that may be another problem in these days, but this is a very new technique because there is a possibility we can reduce the information. We may reduce the size of the information a lot. Okay, this was today's class. We talked about image compression. I first talked about the traditional method of image compression, and finally I briefly explained the compression method of utilizing deep learning. Thank you very much. See you next time.